this is the second TNA review from UCL. So again, I'm going to give you an overview of two of our transnational access visits. The two other ones on the screen there. The first one's called Virtual Crowds, Contributing Factor to Presence in Immersive Virtual Environments. And the visiting researcher here was Yorgos Chrysanthou from University of Cyprus. And the second one I'm going to present is Gaze Contingent Multi-Resolution Displays in Human Visual System Research. You can see these are very snappy titles. And here the visiting researcher was Santiago Martín from the University of Oviedo in Spain. We've hosted many TNA visits at UCL. We've still got a few to complete. So I had a bit of a choice, and my reason for choosing these two was largely on the basis that they had, well, what seemed to me very clearly defined tasks that I felt competent to explain here, and also that neither of these has been presented either, well, they haven't been presented at previous TNA seminars, nor have they been presented at any of the General Assembly meetings before either, or not to my knowledge anyway. In both cases, the researchers involved used the cave at UCL. That was the main facility that they wanted to use, but they used it in very different ways. So these projects are very different from each other. The first one was investigating presence and how this is affected by different levels of interaction with virtual characters. And the second one was continuing an exploration of novel rendering techniques, and the applications for this are in optometry and visual science. So again, both cases, Yorgos and Santiago both had some familiarity with working in a cave, but neither had this facility at their own institution. TNA accesses at UCL are 10 days, so we each had 10 days, and I think in both cases these projects managed the time very, very effectively to get a lot out of their visits. Okay, and just a quick slide showing how I'm going to present each of these talks. So it's going to be a fairly similar structure for each of them. I'll describe the general outline of the proposed research activity, a description of what it was at UCL that they needed to use for their research, what we had to provide them with, then a bit of background and motivation, why the visitor wanted to do this research, and how our equipment and our expertise enabled this. And then I'll describe what happened, how the research progressed over the 10 days, and finally what the outcomes of these research projects were, and any planned future activities arising from them. So the first one I'm going to cover is Yorgos 1, Virtual Crowds. The goal of this project was to allow the development of more sophisticated behavioral models for virtual characters in a crowd simulation. The progress in graphics hardware over the past 15 years, as well as developments in software technology, have allowed us to use fairly realistic animated humans, and they're within pretty easy reach of most developers. You can buy these things online, you can buy these characters ready rigged, and just use them in a modern game engine. However, adding behavior to these characters is still a slow and painstaking process. It's better than it used to be, but it still takes a big investment of work and time and the results can be questionable sometimes. So the goal of this project was to investigate how far a developer needs to go when implementing a virtual crowd in an immersive environment. What sort of characteristics do you want are important to include, and what sort of things can you get away with? And this has kind of been a working practice in the development of VR for some time. You need to know from very low level, psychophysically even, what you can get away with and what you absolutely need to have in there. So it's kind of taking this approach in a very high level to how we develop models for behavioral models for virtual crowds. The main resource required at UCL was Arcade, of course. Full display surfaces. This is a very standard design of Cave. 3 vertical walls on the floor. The walls are back projected. The floor is projected from above. We have InterSense tracking to track the user's head position and orientation. Very high accuracy, low latency. For the application, we also needed a navigation device. This was also using an InterSense wand, and we used the joystick of this for navigation. The other thing required for this scenario was Unity 3D. Our visiting researcher had already developed their scenario away from UCL, and they tested it in Cyprus. So it was important that this application was going to work as soon as they arrived here, with not too much recoding. So for Arcade, we have a number of different systems that drive it. In this case, we used a single large PC with a K5000 graphics card, so single PC with 4 separate synced graphics outputs to drive the 4 displays of the cave, and then we could run Unity on this. Tracking was handled by middlevr middleware, which receives the tracking from a VRPN server. Okay, that's the kind of technical background resources. The motivation for the research. So the main motivation was to understand the conditions that enhance or even detract from presence in virtual environments containing many virtual characters. So this term presence is a quality that we seek to elicit in users of VR systems. It's a tricky term, presence. It doesn't really have a strict definition, and it has, well, possibly has many definitions. So I'm quickly going to switch to a slide that gives a background of how I view presence, or kind of a combination of how I view it and how Yorgos viewed it. So presence is a term sometimes used to denote the feeling of being there in a virtual environment. But it's hard to pin down a definition of this being there quality, and the term is often used to describe phenomena that I would see as being quite different. I would describe it thus. To feel present, you need to have some level of immersion of the senses, so you need to have the wide field of view and preferably stimulation of other senses. The actual feeling of presence is where you act in the simulated environment in the same way that you would if it were a real place. So this is not the same thing as believing that our virtual presented scenario is real, but it's that you will act and behave as if it is. If you feel present, you should become unaware of the technology supporting the illusion, be aware only of the simulated world. So for example, in the cave, you might become very quickly unaware of the actual physical space of the laboratory and sense only the dimensions of the physical space. And if this spatial illusion takes hold very quickly, we quite often see people just walk into the screens accidentally. That's a good example of feeling present. Obviously, walking into the screen breaks that illusion. Another aspect of the overall illusion of presence is the social dimension of your virtual experience. So this is what applies when you have a virtual environment that contains virtual representations of people. These might be avatars representing the live actions of a real person at a remote location. Alternatively, they might be controlled by pre-recorded animation scripts, either triggered automatically or puppeteered by a human operator to give the impression of interactivity. But however they're presented, in all cases you might experience what's sometimes called social presence. So in your actions you would have the feeling that you're engaging or interacting with a real person. In other words, if a virtual character comes up and speaks to you, do you respond? If they walk up too close to you, do you back off and maintain a comfortable social space? These are the kind of things that phenomena you would associate with social presence. Do you have feelings of empathy or trust or suspicion? Do you ascribe the qualities you would normally attribute only to a real person? So that's possibly an overlong overview of the notion of presence, but that's the fundamental to the background of the research. So coming back to the motivation slide, many of the conditions for presence are quite well understood. So I mentioned before that systems should be as immersive as possible, wide field of view, high resolution, multi-sensory, have audio and vision. Update rate should be high, latency of tracking, interaction should be low. These kinds of things are well known. What we also know is that the use of virtual characters presents a different aspect of this, and these differences will manifest themselves in much more sophisticated and subtle ways than we can easily identify. So it will be the ways in which we interpret movements, expressions, intentions of people in the real world. How do we map this understanding onto the virtual characters, and how well does their behavior support this? So human behavior is very, very subtle, as well as having the technical difficulty of capturing and reproducing it. We could use motion capture for this, but there are various problems when trying to include your virtual characters in a scene. If you take motion capture and apply it to arbitrary characters, you don't always get the results you're looking for. Some of the movements might look slightly awkward, and even if it doesn't look right, even in a very small way, then it can be interpreted as weird or unsettling. So this is a problem that's held back the large-scale use of virtual characters in VR scenarios, where you have crowds of people, and where they are implemented, they tend to exhibit only simple behaviors, because we don't have the know-how to make them appear properly interactive like a real person. So the implementation of these more sophisticated behaviors represents a big overhead. So the overarching motivation for this research is to try to identify how people respond to different levels of behavior exhibited by a crowd of virtual characters in a virtual environment. So the objectives for this TNA are fairly straightforward. First of all, we want to implement the Unity 3D scenario in the cave, get it working. This meant interfacing the existing code with middle VR, to get the necessary head tracking, navigation data to all the displays. And then once the application was successfully running in the cave, we wanted to run trials of the experiment, gauging the level of interaction of the virtual characters with participants. So a major goal here was to run a study. As I'm sure you all know, this is time consuming, so when you try to incorporate this into a 10-day TNA, you really need to have things set up quickly. For each trial, what we were trying to do was subjectively assess levels of presence, so that after each trial there was an online questionnaire assessment, largely based on the Whitmer and Singer presence questionnaire. Some details of the experiment. So what actually happened? Well, we had 20 participants taking part in the experiment, each performing 3 variations of the task. The design of the experiment was repeated measures within group, so all 20 participants were tested with all 3 levels of interaction, and obviously these were randomized. The scenario you can see on in the image in the slide was a shopping mall populated by 33 animated characters. Each character had different appearances and behaviors, so different motion captures were used for the different characters. This is important. You don't want to see them walking about all having exactly the same kind of movements, because then they start looking like they start to look like an army of robots. So we've got a screenshot of the scenario there. The task for the participants was to use the joystick to navigate through the virtual crowd. So you can see this shopping mall here. It's kind of like a long wide corridor, and we had to follow a small girl. You can see the character of the small girl just to the right of the participant silhouette in the image. The small girl character was deliberately rendered in a more cartoonish way to make her distinct and easy to see in the crowd. The instructions to the participants were to try and stay at a close distance to the child all times, navigating through the virtual world with a joystick. And the virtual child was also programmed to sing a song as she walked through the shopping mall. So that was another means of being able to hear where she was. And the other characters, while you were following the child through the scene, the other characters would be walking in the opposite direction towards you. And each trial presents a different level of interaction from the other virtual characters in the crowd, the ones who are walking towards you. The first level was really no level of interaction, no collision avoidance, so the virtual characters would make no effort to avoid walking into you. So you could try and avoid walking into them, they wouldn't make any effort to avoid walking into you. In the second level, there was collision avoidance, so the virtual characters would try to avoid walking into you, and this is achieved simply by getting them to avoid the space around where your head tracker is. And finally, the most interactive level, you would have collision avoidance as above, but the characters would also greet you and look at you as they walk by, give you some sort of salutation. Then if I go back, yeah, you can see in the screenshot the guy in the orange t-shirt is hand raised, waving to you, looking at you as he goes by, and probably shouting hello. So, okay, that was the task. The outcomes of all this. So, after each scenario, the participants were asked to fill in a web-based questionnaire. And as I said, this is based on the Whitmer and Singer Presence Questionnaire. Some of the questions talked about the virtual humans' awareness of each other and of the participants' presence. So, and others asked about just more generally about the realism of the virtual environment and the characters in it. So these results were combined and they were compared with data gathered from a similar study performed using a semi-immersive system. So this was in Cyprus. It was a smaller system, narrow field of view, fewer displays, and no stereo viewing. This was done out with Visionair. And the data analysis pointed to a significant correlation between measures of presence with interaction levels of the virtual characters. I can't go into any more detail about this. The detailed analysis is currently being submitted for publication. So that's as far as I can take it with this TNA, but we successfully carried out an experiment and we achieved some useful data from it. The second TNA I'm going to describe is titled Gaze Contingent Multi-Resolution Displays in Human Visual System Research. This was performed by Santiago Martin from the University of Oviedo. Now this work builds on a previous TNA visit. Santiago came to visit us in 2012, where he installed his Gaze Contingent software library in the cave at UCL. So that was a largely successful visit, and on the basis of that he applied again and he was given another 2 weeks to develop this further. So this library, the graphic library stereo vision engine, GLSVE, is an open source C# library based on OpenGL, and it uses vertex and fragment shader programming to help create gaze contingent renderings. So it gives you some detailed control over how you produce your stereo views and different types of rendering effects for blur, depth of field simulation, these kinds of things. So in particular, it enables the development of a rendering system based on gaze direction. So the idea is that human vision doesn't see visual detail evenly all the way across the visual field, so spatial acuity deteriorates very quickly away from the center of view. Likewise, color perception disappears away from the center of view. So for this reason, we might want to alter the level of detail in peripheral regions that we're rendering to. Now, the existing system, as developed from the previous TNA, only got as far as using head tracking data to moderate this. So one of the main aims was this time was to supplement this with the addition of eye tracking data. Equipment and resources required at UCL. Well, again, the cave, I'm not going to describe it again, I just did for the previous TNA. What we also needed was our Arrington eye tracking system. What I would mention about the cave actually is that for this TNA we didn't use a single machine. We implemented the GLSVE library on our 5-node cluster of machines rather than a single machine. The reason for this simply was that this is the platform where the initial development had taken place, and it seemed easier to continue developing on this platform. So the eye tracking system we have, Arrington Viewpoint Eye Tracker, it uses infrared illumination and cameras pointed towards the eyes to detect and measure corneal reflections. And these same camera images can also be used to detect changes in pupil size via an adjustable thresholding system. So the way it computes gaze direction is just the vector from the center of the pupil to the center of the corneal reflection, and this is used as an input to an algorithm that computes gaze direction. This is a proprietary algorithm of Harrington. There's also an outward-facing camera that you can see in the image there. The outward-facing camera captures 2D image of the user's field of view, and so you can map the gaze path onto the outward-facing camera. Another qualitative system is that it works, and this is very important for us, in low light levels, and it works through LCD shutter glasses. So you see in the setup here, we have the cameras pointing through shutter glasses at the user's eyes. So this means that we can use it in the cave. Okay, the motivation for the research. So the background of this research lies in the disjunction between how the visual system processes visual information and how we typically display visual information with computer graphics systems. Human vision subtends wide field of view and provides high resolution detail at the center of gaze, with decreasing resolution in the periphery. The fovea, this is where our central vision is less than 1% of retinal size. It takes up over 50% of the visual cortex in the brain. So you can see this is the far more important region, and maybe we could focus more of our effort rendering towards where the fovea is pointed, where our gaze is fixated. Photoreceptor cells in the fovea are almost exclusively cones. Outside the fovea they are rods. The rod cells don't provide color vision, and they function mostly in dim light with limited spatial resolution. So this is a characteristic of human vision that suggests that we should invest most of our computing power to render the foveal area, limited computing resources to draw lower resolution images in the periphery. But this is universally not what we do. This would allow us to reorient computational load, especially if you have a wide field of view system like a cave. So this is a recognized field of study. It's often referred to as gaze contingent multi-resolution display for this approach to computer graphics. In addition to the obvious implications for efficiency, the research also has direct application to psychophysical studies of the human visual system. Just to go over where we got to with the previous study at UCL, this is the previous TNA in 2012. The library was successfully implemented in UCL Cave. We managed to run some tests using head tracking to moderate gaze contingent rendering, and to test again computational loads with, obviously at the moment with this stage of the engine, it doesn't perform rendering particularly efficiently. It's using things like Gaussian filters, so actually there can be some overhead to the rendering. This is more the proof of concept stage. We weren't able to gather eye tracking data. This was simply due to a technical failure of the eye tracker. I'm not going to go into the details of this, but just to really highlight that this is one of the hazards of TNA research, in that no matter how much pre-preparation we do for these, there's always a possibility that something might go wrong with an important piece of equipment. Fortunately, that's the only time that's happened to us. But because we only have 2 weeks, you don't really have the luxury of time to repair the system or devise a workaround. In fact, we had a problem with the eye tracker this time round as well. Fortunately, it was something that was resolved within a couple of hours. So, in spite of the problem with the eye tracker and the initial TNA visit, we were able to test the software library based on head tracking data only, and these results were presented by Santiago Martin at the International Conference of Behavioral Optometry in Birmingham a few weeks ago. So the objectives for the current TNA, these are well described in the work plan, and like I say, pre-preparation is always key with these TNAs, so this helps smooth the ground for this. The first goal was to get the eye tracker working and allow the streaming of eye tracking data to the GLSVE library. So the first thing we need to do was get the hardware set up and get its data flowing to the library that we had. We then wanted to get a good physical setup of the eye tracker. So because we're rendering based on gaze direction, we want to have a very, very stable system and a very accurate system. And we want to be able to measure this accuracy as well. And then once we'd achieved some desired standard of accuracy, I'm not sure what that was, but Santiago was happy to go ahead, and we designed an experimental setup to measure how convergence of the eyes can reduce visual acuity in objects that are positioned in frontal and behind the fixation point. So this is why we needed to have something stereo setup with a wide field of view, because obviously we're trying to do this in a gaze contingent way. And we want to see if we get people to force people to fixate on an object, what happens to objects presented in front of or behind the fixation point. So we want to do that and then apply these findings to the graphics library to allow depth of field effects away from the fixation point. So what we actually did, well, first of all, we had assumed that the metal frame, this is the one on the left here, that I showed before, this is something that had been custom built for a previous project at UCL, and we had assumed that being solid and metal, it would provide a good solid rigid frame and would provide robust and consistent data. In particular, it would prevent the cameras moving in relation to the eyes, because this is the biggest problem. You can see the cameras in the left-hand image pointing into the eye. So for each eye, there's a infrared light to illuminate the eye, and a camera as well. And so it's very important that these don't move relative to the eye, otherwise your data is going to become very, very noisy. But what we found was in practice, this metal frame really didn't work very well at all. And that there was far too much movement of the cameras relative to the eyes. Unless the frame, the only way we could get around this was by attaching the frame to the head so tightly that it became extremely uncomfortable to wear for longer than a few seconds. So this is unworkable. So what we had to do was redesign the mounting of the eye tracker, and first we were bearing in mind that we didn't actually need to use the outward facing camera. We didn't need to have a view of where the user was looking, so we removed that completely, and we ended up with a much lighter design that you see on the right, and this is just attaching the eye tracker to an unmodified pair of shutter glasses. This is the part of the process where we managed to also sever one of the eye tracker's cables. So this is where we had a few nervous hours until we were rescued by soldering efforts of another staff member here. So once we had the eye tracker working, providing stable and accurate data, we could do all that with the Arrington software. We then used VRPN to get data from the eye tracker served to the GLSVE library. Okay, so outcomes of this research. Well, there's a screenshot on the right-hand side that requires some explanation. What you can see is in the top half of the visual field is the actual environment, and in the bottom half is a very, very crude visual effect. So what the new system does is it combines the eye tracking and the head tracking to alter rendering around the fixation point. So you can see the center of the fixation point is the center of those concentric rings there. We did some proof of concept tests in the cave, the user would need to work to track a small sphere as it moved in space in the 3D environment. So you can see the small sphere at the gaze point there, and they would need to track that with a small cube, and the small cube they could control with the InterSense joystick, so they could move it around, they could move it up and down from one plane, it would automatically go to the right Z plane. So this is the task they would have to do, and this was to help, the purpose of this task was to help keep the users fixated on this point and not get distracted. While this was happening, blurring, and these are the crude effects you see here, would occur in either the upper or lower visual field. And also occasionally there would be a bell sound that would come through the audio system. And at this point, every time you heard the bell, the user would have to press either the upper or lower button on the InterSense wand to report which field the blurring had taken place in. So if it was in the upper half of the field of view, they would press the top button, lower half of the field of view, they would press the lower button. Now, I know to look at the image, it looks like this is an extremely easy task. In fact, it was an extremely difficult task to perform. Certainly when I did this, I quite often had to guess my responses. So there wasn't sufficient time to conduct proper user trials, so we remained at the proof of concept, but with an enhanced system. We do have plans to continue this development next year. We're going to try and seek some funding for this. Some of the work that's still required is a redesign of the experimental interface to reduce complexity. So the idea that we had was to have a cognitive load, a cognitive task to keep the user fixated on the sphere that represented the center of that would move to the center of their gaze, or to keep the center of their gaze on this sphere. What we found actually is that the cognitive load of that task is possibly a bit high, hence the task was quite difficult to perform. So this should be an easy problem to solve. It should be easier to reduce the complexity of this task. It would have been harder had it been the other way around. And if we can do that, then we would move ahead with a user study.